Hello, my name is Michael Glinsky of BNZ Energy Incorporated. I am going to present to you the content of a manuscript entitled High Gain Fusion Target Design Using Generative Artificial Intelligence that is out on the archive. We are returning to topological basics. The topic of my UCSD oral qualifying exam in theoretical plasma physics, examination committee chaired by Marshall Rosenbluth in the second floor Mayer Hall conference room, inspired by Ted Frankel's class in The Geometry of Physics, and in collaboration with Michael Friedman. This is Taylor relaxation to a topological singularity with helicity conservation as energy, the weak Noether invariant, is dissipated to an external system. This is only a metastable point, an X point, so that the system needs to be ponderomotively stabilized. The X point is a local maximum that can be stabilized from both minor and major disruptions. This is the basis of design of tokamaks, stellarators, Z-pinches, and reversed field pinches, and the physics of stellar structure and metastability. Stars are entangled balls of yarn, helicity. Minor solar disruptions are solar flares. Major solar disruptions are supernovas. Minor tokamak disruptions at the separatrix lead to anomalous diffusion of energy to the plasma wall. Major disruptions of the H mode leads to plasma disassembly. Topology can be viewed as the mathematics of knot tying. Think about tying the knot as shown. Take two strings, tie one into a loop, twist the second string around the first, tie the second string into a loop. Now deform the knot manifold into a double helix, a torus, two counter-rotating double helices, and further entangle the knot into a four braid. The double helix is the deformation of a Z-pinch plasma. The torus is the deformation of tokamaks and stellarators, and the four braid is the deformation of a laser reverse field pinch, to be discussed in detail next. This should look familiar to those of you familiar with the deep reinforcement learning or the DeepQ networks used by DeepMind in the AlphaGo and AlphaFold products. A shrinkage to an optimum. Control is forcing the system to the optimum X point, then ponderomotively stabilizing that X point, tying the knot, then stabilizing the knot, keeping the knot compact. How do you tie the plasma in knots and keep them compact? This is the job of Ubuntu Fusion Target and Drive Design. Shown on the left is what happens if the plasma is not tied into a knot. That is, it has no helicity. To its right is a plasma in a Z-pinch that is tied in a knot. That is, it has helicity. Without helicity, there is a normal turbulent cascade of the Rayleigh-Taylor or Rickmeyer-Meshkov instability, forming a mixed layer of dimension of a millimeter or two, determined by the wavelength of the fastest growing mode of the instability, in both the axial and radial directions, with a bubble and spike behavior, that is, periodic singularities. With helicity, there is an inverse cascade, that is, there is no mix, into a self-organized structure of a twisted pair with an axial structure, that is, periodic singularities, whose dominant axial scale is the maximum growing wavelength of the instability, that is, a millimeter or two. On the right-hand side is the target and drive of the proposed laser Z-pinch at room temperature and pressure. Shown is a cylinder of beryllium coated on the inside with a solid fuel, that is lithium 6-deuteride or HB11 at room temperature, that while more challenging to ignite than DT ice, is capable of giving significantly more yield. On the inside is a DT gas igniter that will be compressed by the cylinder as it implodes, driven by the magnetic pressure generated by the absorption of the laser in the candy cane stripe pattern, shaped by the appropriate phase plates. The stagnation of the liner will be a twisted pair of strings about 200 microns in diameter, with the stagnation of the igniter being a twisted pair of strings at the center of the liner strings, 20 microns in diameter, separated by about 200 microns, with axial spots forming every millimeter or two at the singularities, shown by the orange image, that is, a self-emission image from the Z machine. The image shown is prevented from forming the spots because the plasma was preheated by a laser to 300 volts. The two strings of the stagnated igniter will be surrounded by the tornado of the cylindrical shell of the solid fuel about 500 microns in diameter. The tornado shown was generated by Dali, and to the right of the core shown is a backlit image of the Z-pinch plasma at the University of Michigan. Since there is a very efficient, that is, with a very high implosion velocity, stable 3D spherical implosion of the igniter will be able to ignite and burn the solid fuel, first in a spherical manner until the spheres coalesce, then in a cylindrical manner. Shown on the right-hand side is the knot tied in the plasma. There will be very large helical magnetic fields at stagnation in excess of 10 kilotesla, reducing the radial heat flow and alpha transport, confining the burn to the imploded fuel. The dimensions and shape of the target and the pattern, spatial and temporal, of the laser will be designed by Ubuntu Gen AI to optimize the yield. Up to now, inertial confinement fusion using lasers has only uniformly driven the targets without helicity. Given that the targets are compressed about a factor of 10 in linear dimension, unless the targets are initially more than a few centimeters in size, the mix layer thickness will be larger than the compressed target. The igniter will be mixed with the fuel. This can be prevented by helically twisting the laser drive. ICF capsules have been compressed by ablative or radiation pressure. That is a constant as the target implodes. This new design converts the laser energy to magnetic field energy, then drives the implosion with magnetic pressure, which increases as the target implodes from megabars to tens of gigabars. Let's take a closer look at the details of the laser drive. Shown on the left is the drive of the laser Z-pinch shown on the previous slide. Shown on the right is the more practical laser RFP. 4 laser beams shaped by phase plates about 1 centimeter in diameter impinge on the target in a plane perpendicular to the axis of the target cylinder from the north, south, east, and west. Therefore, there needs to be no physical contact with the target to deliver the energy, and only 4 very small access ports. The Z-pinch geometry does require 2 handles on the target to provide a path for the return current, complicating the target and making it more difficult to fabricate. There also needs to be no conductor across the top and bottom, further complicating the target and making it even more difficult to fabricate. The base laser illumination pattern is a helical candy stripe. The RFP geometry does not require the handles for the return current. Instead, a beryllium top and bottom needs to be put on the cylinder, making it into an enclosed can. The base laser illumination pattern is a crisscrossing double candy cane or braided pattern. Note that this target will be at room temperature, not at cryogenic temperatures, making it much more practical. The target is simply a low tolerance, about a tolerance of 2% can, with top and bottoms, coated on the inside with solid fuel and filled with DT gas, in the case of the laser RFP. This is an extremely simple, practical target that is very easy to fabricate. Significant defects like cracks in the can will be self-annealed by the self-organization of the inverse turbulent cascade. Here are the 10 pieces of evidence, 6 of them published, heretofore unexplained by theory, supporting the theory behind a Butu fusion target and drive design. This is similar to how the special theory of relativity explained the Michelson-Morley experiment. The stagnations of the maglev experiments always form a twisted pair with an axial sausaging, but only if the plasma is driven to have a significant amount of helicity. The plasma is compressed from the initial 1 centimeter dimension to 2 helical strands about 2 microns in diameter, separated by about 200 microns, a convergence ratio of 200. This can only happen if there is an inverse cascade, leading to self-organization. There is a 10x variation of yield for nominally similar Z-shots, probably due to small variations in target and drive that seed the natural helical topological modes. There is better performance for large aspect ratio targets because natural topological modes grow faster. And there is poor performance of the dielectric coated targets because natural topological modes grow slower. Experiments at the University of Michigan have tracked the mode merger and the inverse cascade. The last 5 pieces of evidence can be found in simulations. The data science group at Lawrence Livermore National Laboratory, when they optimized the 2D laser ICF target design, found that the optimum metastable design was a laser RFP yielding a quadrupole stagnation consisting of 4 vortices. A group at the Laboratory for Laser Energetics, when they simulated their hybrid laser target in 2D, found that they achieved a laser RFP stagnation. A group at the Osaka Laser Lab, when they simulated a short pulse laser target in 2D, found that they achieved an RFP stagnation. Shipley et al. At Los Alamos National Laboratory, when they simulated an Automag Z-pinch in 3D, found that it had 2 times the yield of an equivalent maglev target. Finally, Glinsky and Monpan, when they simulated an ensemble in the 2D plane perpendicular to the Z-pinch axis, found that the stagnation always consisted of 2 vortices whose orientation was set by the initial m=2 perturbation. No matter the size of that perturbation, and there was an inverse cascade, consistent with the Z-pinch twisted pair topology in 3D. Note that the self-organization in the 2D simulations came from the conservation of the vorticity topological invariant. To maintain metastability in 3D, the targets or drive will need to be twisted in the axial direction in order to have the helicity topological invariant. This design philosophy leads to more aggressive high aspect ratio targets, no suppression of natural topological modes by things like dielectric layers or dynamical screw pinches, no laser preheat of the DT gas so that the gas implodes on a much more aggressive adiabat, more efficient use of the drive energy, since the drive energy is concentrated at the natural topological modes. Much better ignition and burn propagation, burning the more efficient and practical solid fuel, that is, lithium 6 deuteride or HB11 instead of DTIs. Low tolerance and simple targets for inexpensive target fabrication. And most importantly, no turbulent mixing due to the inverse cascade. Existing simulations and experiments indicate that the fuel can be assembled, ignition conditions might well be obtained in the igniter, and conditions can be obtained for an efficient 2D burn of the fuel using as little as 3 megajoules of energy on target. The yield could be up to 10 megajoules, which is the expected yield from the imploded liner material, demonstrated in maglev experiments, if the imploded fuel is burned completely. As stated by Deep Thought in A Hitchhiker's Guide to the Galaxy, it is most important to know what the question is, not the answer to the question. The following series of slides are a series of questions. Tom O'Neill, when he taught the graduate EM course, taught the course from the perspective of Landau and Lifshitz, not Jackson, to change the intellectual paradigm to one with more theoretical potential. We need to approach fusion target and drive design from the perspective of nonlinear, not linear plasma physics. We need to be good parents and encourage the plasma to mature and become its own person. Instead of integrating the unstable field equations justified by ad hoc arguments, and requiring draconian resistive L2 regularization of the unstable singularities. The action, which is single valued, guaranteed to exist, and a minimal surface, should be found by variational techniques. This is theory based on geodesic motion, coming from variational minimization of action that does not require regularization. The current theory of artificial intelligence, based on the work of John Hopfield, views AI as a web of connections of nodes organized into layers, with the connections graph engines connecting one layer to the next. The system is assumed to be in statistical equilibrium and is called a Boltzmann machine. Do you know what this is? I don't. Instead of using this graph paradigm, we view AI as model estimation by a piecewise linear universal function or functional model that is estimating a function or functional with C0 continuity, but no more. That is a minimal surface with cusp-like singularities. This model has thousands of parameters for a function and trillions of parameters for a functional, but for a functional, that is not near enough. The system is assumed to be canonical in only dynamical equilibrium, not in statistical equilibrium. It is a question of physical kinetics, not statistical mechanics. Generative artificial intelligence is not generating a statistical ensemble. Generative artificial intelligence is generating the canonical motion of a collective system. The concept of dynamical equilibrium and the evolution to statistical equilibrium was taught to me by Tom O'Neill in the graduate plasma physics course he taught at UCSD. What is the functional and function that generative artificial intelligence is estimating? It is the action, also known as entropy, log likelihood, the approximate Q function of DeepMind's AlphaGo and AlphaFold, and the approximate score function of OpenAI's ChatGPT. The functional is the canonical generating functional of a canonical transformation from the canonical field momentums and fields of the collective system to the canonical momentums and coordinates of the system, that is, the reduced order model. The function is the canonical generating function of a canonical transformation from the canonical momentums and coordinates of the reduced order model to the canonical momentums and coordinates where the evolution is linear. The modern systems control theory of Kalman and Bellman, developed in the late 1950s, is based on the Hamilton-Jacobi equation. We extend their theory to collective systems and the functional form of the Hamilton-Jacobi equation. The Bellman equation, as a discrete form of the Hamilton-Jacobi equation with dissipation, is called in systems control theory, is solved in the deep Q networks of deep reinforcement learning of AlphaGo, as indicated on the first slide. Current generative artificial intelligence solves the Hamilton-Jacobi equation by introducing a significant amount of diffusion that drives the system to statistical equilibrium. They call this a diffusion model. It solves for the ensemble in statistical equilibrium by using the metropolis, better known as the Rosenbluth method. This significantly degrades the performance. It sacrifices performance for stability and solvability. Conservative systems have as many unstable roots as stable ones. The unstable x-points or singularities are the desired ones, but they are destroyed by this large amount of L2 regularization. Instead, we calculate the non-stationary singularity spectrums of a system that is not in statistical equilibrium by calculating the coefficients of the functional Taylor expansion of the action, also known as the S matrix, M-body scattering cross sections, and M-body Green's functions. We derived a formula for this functional that has a fast n log n computer implementation of the forward and inverse transformations. It has the form of an iterative wavelet transformation interleaved with the Green's function of a complex variable. This is new, the Heisenberg scattering transformation. It is a logical mathematical process of renormalization based on calculating the S matrix of Heisenberg's canonical approach to field theory. It is a non-stationary, that is local, Fourier spectrum, or the non-stationary spectrums that are the solutions to the renormalization group equations. In this momentum basis, whose basis vectors are given by these non-stationary spectrums, the action, a generating function, a minimal surface, and the solution to the Hamilton-Jacobi equation can be approximated by a multi-layer perceptron with rectified linear unit activation. The HST has the structure of a deep convolutional neural network. It is a series of convolutional layers interleaved with an activation function. Furthermore, the real part of the Green's function, the activation function for small argument, is a two-sided rectified linear unit. The results are then pooled to form a reduced order model. Each convolutional layer scatters the signal. The HST can be viewed as the multiple scattering of a signal to all orders. This is the transformation, the transformer, that a generative pre-trained transformer is pre-training. The African philosophy of Ubuntu is based on the interconnectedness of society that leads to a conservative collective system with canonical structure that is a symplectic geometry. Given this logical mathematical process that is Ubuntu Gen AI, the collective system, the society, can be controlled. The topology of the plasma can be optimized and stabilized. Another way of looking at the HST is as a deep deconvolution of the multiple reflection of the individual, the spirit of Ubuntu, who is multiply reflected into the collective, that is, society. By the way, collectives are fields or swarms of elementary particles making elementary fields, charged particles making plasmas, molecules making fluids, celestial bodies making cosmoses, economic entities making economies, persons making societies, and so on. The HST avoids the additional BBGKY expansion in the weakness of correlation that leads to infinities that need to be removed by renormalization. It calculates the local, non-stationary singularity spectrums using a principal components analysis, also known as the renormalization spectrums. Riemann moduli, or topological indices of the Riemann surface or manifold, the cotangent bundle of the dynamics. Generative artificial intelligence is a two-stage canonical autoencoder that is a controller of collective systems. Its input is a measurement of the fields, and its output is the force field of control. The first stage is the Heisenberg scattering transformation, followed by a principal components analysis, giving the reduced order model. It is not a deep convolutional neural network with trillions of parameters as in DQ networks and generative pre-trained transformers. The second stage is a multi-layer perceptron with rectified linear unit activation with only thousands of parameters that estimates the canonical generating function. This forms the two-stage decoder. It is followed by a two-stage encoder. This approach to AI is solving a system of partial differential equations by a functional transformation to a domain where the motion is trivial, that is linear, then transforming back. It also can be viewed as topological characterization and control. The two-stage canonical autoencoder is finding the analytic function whose Riemann surface, that is manifold, has topology of the collective system, its cotangent bundle, and whose non-stationary singularity spectrums are the Riemann moduli or topological indices, that is the integral of this Chern-Simons 3 form of the collective system. The circuitry of the HST plus PCA is most likely found in the primary visual cortex of the brain, and the circuitry of the MLP with rectified linear unit is most likely found in the prefrontal cortex of the brain. The core innovation is replacing the deep convolutional neural network of today's generative artificial intelligence, which has trillions of parameters, with the Heisenberg scattering transformation, which does not have any parameters. The resulting Ubuntu Gen AI is a controller of collective systems that optimizes the performance of the collective system and ponderamotively stabilizes the collective system so that it does not disrupt. Glinsky and Maupin were able to train an MHD surrogate using a preliminary version of this new theory in 20 core seconds using 500 2D simulations. The high-fidelity surrogate could simulate the system in 1 core second, where traditional finite element methods would take 240 core hours. For a 3D simulation, traditional methods would take over 100,000 core hours. The singular valued decomposition of the cross-variance matrix showed a 1-to-1 mapping between the principal components, that is, the renormalization spectrums, and the initial conditions. A remarkable result that gives physical meaning to the renormalization spectrums. This is another whole talk. See the links to the paper on the archive and YouTube video of the talk. The HST is a logical mathematical process of renormalization as requested by Dirac. There's another whole talk about how this is a new theory of plasma physics and a new field theory. It is an alternative to the BBGKY theory of plasmas and the perturbation theory of fields, both of which make mistakes. They expand the terms of the mirror cluster expansion in terms of the plasma correlation parameter and the field coupling parameter. The convergence goes from superconvergent to a very weak asymptotic convergence, leading to the divergence, the infinities, in current methods of renormalization. The expansion parameters are many times not less than 1. See the links to the paper on the archive and accompanying YouTube video of the talk for the details. A postscript. Ubuntu GenAI is a very powerful tool in model estimation. This emanates from linkage of the form of the Lagrangian, function and functional form, and the non-stationary spectrums that are found by the HST plus PCA. A 1-to-1 correspondence. Unique. There are only a limited number of terms that can appear in the Lagrangian, so there will be a limited library of non-stationary spectrums, and by cross-correlation to the coupling constants, that 1-to-1 correspondence can be found, as was done by Glinsky and Maupin. This is further evidenced by the transfer learning of the pre-training of a GPT from language to fluid dynamics, for instance. Now, when the theory is compared to experiment, one can determine the number of non-stationary spectrums and what those non-stationary spectrums are in the experiment by determining the number of significant principal values and determining what the principal vectors are associated with those significant principal values. One can also do the same exercise with the theory. Discrepancies between the theory and the experiment will show if a term is missing in the theory or if a term is incorrect in the theory. The theory should extrapolate well in the scale of the fields, just so the experiments are being extrapolated away from the non-stationary singularity spectrums in the theory, not extrapolated towards a non-stationary singularity spectrum that is not in the theory. There's a simple test for this. Conduct a series of experiments at different scales of the field. Examine the systematic deviation of the experimental results from the theoretical predictions. If the deviation gets less as the scale moves in the direction of extrapolation, then the theory is sufficient. If the deviation gets more as the scale moves in the direction of extrapolation, then the theory is deficient. Now for some fun bonus material. Ubuntu GenAI is at the intersection of mathematics, physics, and AI. It is a true cross-fertilization. It is bilateral, not one way. Successful methods of generative artificial intelligence, that is GPTs, DQ networks, and the scattering transformation, gave clues to the solution to both an outstanding math problem, that is a topological metric, and an outstanding physics problem. That is a logical mathematical process of renormalization identified by Dirac. Meanwhile, mathematics, that is topology, exterior calculus, symplectic geometry, and Lie groups, combined with physics, that is the action, the generating function of a canonical transformation, the S matrix of Heisenberg's canonical approach to field theory, renormalization, nonlinear dynamics, complex systems, and physical kinetics, leads to the geometry of physics. The intersection of the three leads to Ubuntu Gen AI, which is the characterization and control of the topology of collective systems, including physical systems like plasmas, fluids, and elementary fields. The resulting solution, Ubuntu Gen AI, is simple and obvious, that is obvious after the discovery. Truth is simple and obvious. Occam's razor is also found at the intersection of scientific disciplines. The climax of the 1984 movie Ghostbusters is the small thermonuclear explosion caused by crossing the four plasma streams so that they would stably implode into a forebraid. This was the same year that the NOVA laser at Lawrence Livermore National Laboratory achieved first light. NOVA was capable of putting 150 kilojoules on target, enough energy to implode a 3 millimeter Ubuntu target into four twisted plasma streams, yielding 300 megajoules, that is 150 pounds of TNT equivalent of energy. The explosion shown in the movie is about 5,000 pounds of TNT equivalent, which corresponds to a 1 centimeter Ubuntu target yielding 10 gigajoules of energy, driven by 3 megajoules of energy on target, the NIF laser or the Z machine.
Terrified beyond the capacity for rational thought.
Bucket. Church in my town. 1, 2, 3. Funny us going out like this, killed by a 100-foot marshmallow man.
We've been going about this all wrong. This Mr. Stay Puft is okay. He's a sailor. He's in New York. We get this guy laid, we won't have any trouble.
I have a radical idea. The door swings both ways. We could reverse the particle flow through the gate.
How?
We'll cross the streams.
Excuse me, Egon. You said crossing the streams was bad.
Cross the streams.
You're going to endanger us. You're going to endanger our client, the nice lady who paid us in advance before she became a dog.
Not necessarily. There's definitely a very slim chance we'll survive.
I love this plan. I'm excited to get well. Let's do it.
It's definitely not worth $11 a year.
See you on the other side, Ray. I'm with you, Dr. Franklin.
you very much for your attention.